Hi, my name is Muhammad Zubair Wahab, and this topic for this video is pipe bend for the momentum equation. Alright, in the previous video we have done the deflection theory. Alright, and in this video we will concentrate on the pipe bend. Okay. Alright, so before we can apply the equation, it is better for us to start with the basic. Okay, so let's say we have a pipe which have a bend. Alright, which have a bend. So part of this pipe is a bend. Alright, and let's say, alright, so let's assume this is the pipe. Alright, a long pipe. Okay, you have a long pipe. And then at part of this pipe, alright, let's assume you have a bend. Alright, so let's say you have a bend, and at the same time your diameter of the pipe is being reducing. Alright, so you have a reducing bend in this case. Alright, so let's assume the angle of this bend is around what? Let's call it a 30 degree. Alright, and then the fluid is flowing from left to the right again. Alright, okay, so the question is, let's call this as D1, which is bigger than the D2. Alright, let's assume it is bigger than D2, and let's assume it is not the end of the pipe. This is not the end of the pipe. Alright, let's assume it is joining with another pipe, a long pipe there. Okay, so the question is, what is force given by the fluid to this bend? Okay, so the question is, we try to determine what is the value of force acting on the bend because of the fluid moving inside of this particular pipe. Okay, so we are looking for force, and once again, why we have this force? Because why? Because we have a flow which is in a straight pipe, and suddenly the flow is being deflected by a bend. So when you have a deflection, there must be some forces acting on the bend. Okay, so we try to determine what equation should we put into this bend, alright, in order to determine the value of the force, alright, because of the momentum change. And once again, in order to solve this, first of all, alright, please remember the first thing you need to do is to draw boundary or a control volume. Alright, draw a control volume. Let's assume we like to take this part as the part of the control volume, that the control surface, and then assume somewhere here is the second control surface, and the whole set here, alright, the whole set here will become a control volume. Okay, alright, so take this control volume out, alright, take the control volume out and redraw it again. Alright, before you solve it, it is better for you to redraw our control volume. Call it as a 0.1, call that as a 0.2, and you know the fluid is moving on this part 1 or control surface 1, write it as a V1, and there must be a fluid coming out from this bend. Alright, and then call it as a V2. Alright, and then since it is not in X and Y direction, oh, by the way, you need to draw the axis itself. Alright, so draw this in X direction, this is a Y direction. Alright, so we can write it as a V2X, and this is a V2Y. Okay, so now we're talking about fluid flowing inside the pipe. So when the fluid is flowing inside the pipe, alright, there must be a pressure inside the pipe. Alright, there must be a pressure. Alright, so we need to take consideration of this pressure inside of this pipe. So at the point 1 here, there must be a pressure which is I'll call it as a P1. So let's say if you have a P1 somewhere here, so there is a force given by the P1. So we call it as a F1, which is equal to P1 A1. Okay, and then at point 2, which is also inside the pipe, there must be a P2 somewhere here. Alright, so let's say we have a P2 there. Okay, now the P2 which try to resist the motion of the fluid. Alright, so P2 here, alright, P1 will create a force which try to force the fluid to move from left to the right. Okay, a P2 which is also a force will try to reduce the movement of the fluid. Alright, so that's why we said the fluid can only move if we have a pressure difference. So the word is what? Pressure difference. Alright, so what is the pressure difference? Pressure difference is dP. Alright, so all the fluid can only move if we have a pressure difference. So in this case, P1 must be greater than P1 must be greater than P2. Alright, so the word is what? Pressure difference. What it mean by pressure difference? The pressure difference means that your P1 minus P2 must be greater. Alright, so the fluid will move from 1 to 2. So P1 minus P2. So in this case, now what I'm trying to tell you is that because of the pressure difference, so the direction of the force at a point 2 in this case is pointing toward the control volume. Alright, toward the control volume. That is your F2. Alright, so alright, and then put it in X and Y direction. So you have F2X and then F2Y. Okay, why the arrow is pointing inside the control volume? Because the fluid can only move if we have a pressure difference. The word is different. Alright, not the summation of pressure. Alright, not the summation of pressure, but it is a pressure difference. So the arrow must be pointing into the control volume. Okay, and please remember, alright, because the fluid is moving here, so you will have a force, alright, the Fx, the one we are looking for, and also the Fy. Okay, alright, so I think that's all. If alright, if our diagram here is a what? A top view diagram. So let's say this pipe is a top view. Okay, so now, so we need to analyze. Okay, once again, we're looking for the Fx and also the Fy. Okay, so now let's go for the X direction. All right, in X direction, you see that in X direction. In X direction, okay, with the write the momentum equation. We write it as the sum Fb your plus the sum Fs is equal to sum the control surface V rho V dot A. We use this equation because why? Because we assume the flow is steady and uniform. Please remember that. We assume the flow is steady and uniform. Okay, so in the X direction, looking at our free body diagram here, we know the weight. Alright, the weight is in the Z direction, in the Z direction, is right? Because why? Because the X and Y actually is on the ground. Alright, so the Z must be pointing toward the ground. So the G, alright, the gravity or the weight is in the Z direction. So there is no weight in the X direction. So it is 0 plus all the forces that you see in the X direction. First of all, you see what? F1, is it right? And then you see what? The Fx itself. So you have your Fx. Next, you see what? The F2x, alright? The F2x there. You see that? The F2x at the top there. Okay. and you see the direction. Where is the direction? The direction is pointing that side, while your x direction is pointing to the right. So your f2x is opposite of the x direction. So you need to write it as the minus f2x. Alright, minus f2x. Okay, and then do you see any other forces in x direction? That's all right. So it's equal to, and once again, alright, the first step is always write it as the put it in the parentheses, write it as the v rho v dot a, the first control surface, and add another what? Another control surface, v rho v dot a 2. If you have 3 or 4 control surface, don't forget to add. Okay, don't think about the value. What is the value? Don't think about the value. Just think about what? Put it in a bracket. Okay, all right. So if we want to generalize the equation here, if we want to generalize the equation, so all of these we call what? The summation of all forces. All right, this one is what? The summation of all forces. Okay, we are looking for a general equation. So this we can write it as the sum of force in x direction. So is equal to, all right, when you open this equation, you write it as what? v1 in x direction times the rho, and you know that it is a v1 dot a1 plus the v2 in x direction rho, and then you have your v2 dot your a2. And once again, as been mentioned and have been explained it before, the v1 dot a1 is always what? Negative. So we can write it as the v1x rho minus q and plus the v2x rho and time the q. Alright, I didn't put a q1 and didn't put a q2 because why? Because q in equal to q out. So since we only have 1 in 1 out in this figure, so we can write it as the q. So you don't have to mention it whether it is a q1 or whether it is a q2 because both are just the same. Okay, all right, so rearrange the equation. You can write it since you have the same rho q, so you can write the rho q is equal to v2x minus v1x. Is it correct? Right, so because why? Because this the first term there is negative while the second term is positive. So rearrange the equation. Finally you have sum fx in the direction is equal to rho q v2x minus v1x. Okay, and the rho q is also known as what? Mass flow rate. So finally you can write it as sum of the force in x direction is equal to m dot v2x minus v1x. Okay, so this is a general equation for a flow or a pressure or the momentum, change in momentum inside a pipe. All right, inside a pipe. And once again, this equation, all right, or this particular equation represent what? The reaction force. All right, this is represent what? Reaction force. What I mean by reaction force? It is a force from the bend, all right, to the fluid. All right, so this is a bend to the fluid. Okay, if the answer is negative, all right, so if you are looking for a force from a fluid to the bend, so you just change the direction and put it in terms of positive value. Okay, so that's in the x direction. If we go for the y direction, all right, y direction. Okay, write it, the momentum equation again, sum FB plus your sum Fs is equal to some control surface V rho V dot A. Alright, and once again, there is no weight in y direction because the weight in this case is in the z direction, plus, alright, any forces in y direction. How many forces in y direction? Alright, I can see this, the red one here, and the other is the blue one here, alright, the blue. So we only have two. Alright, we only have two, what they call forces. Alright, so one is pointing in y direction, the other one is the opposite of it. So once again, you can write it as the Fy you are looking for minus your F2y is equal to, just write it, rho V dot A. Alright, 1 plus V rho V dot A to V2. Alright, so in this equation, alright, in this particular equation, we know that when you open this as a V1y and rho minus Q and plus the V2y and rho Q. And you know that V1 is not V1, there is no velocity 1 in y direction, right? There is no velocity 1 in y direction. So the first term actually will become 0. Alright, but since we are looking for a general equation, okay, please follow what I'm trying to say here. We are trying to write what? A general equation. Alright, so if you put in the general equation, we can say that sum Fy is equal to once again, alright, your rho Q, okay, your V your V2, alright, is equal to V2y minus V1y. Okay, and once again, alright, so this equation is what? For this equation represent what? Reaction force. Alright, this represent reaction force. So in other words, if you have a z direction, so you have the sum Fz is also the same, rho qv to y minus v1y, or you can write it as what? Sum Fy is equal to m dot, alright, v to y minus v1y. If you want to put it in terms of mass flow rate. Okay, alright, so this is a general equation. Alright, so if you don't like to use this general equation, you can use this what we call the full equation here. Alright, the full equation here. Alright, what I mean a full equation is you derive one by one all this all the data that you have here and put it in terms of the final equation. Okay, and once again, because you have the force in x and y direction, finally of course you need what? The resultant. Alright, so resultant force, don't forget the resultant force, the F resultant is equal to Fx square plus your Fy square, and you square root the both equation. Alright, and the direction of it is equal to inverse tangent your Fy divided by Fx. Okay, so that's the general equation for what? For a flow, alright, or for the change in momentum inside a band. Okay, so we stop here and we will continue with next video of using with numbers.